about stochastic methods for AUC optimization subject to AUC-based fairness constraints. As we all know, machine learning is very useful in high-stakes decision making. However, the problem is that how to avoid unfair AI systems that make discriminatory decisions for protected group, which can be defined by gender or race. So here we consider solve this problem with constraints. So we want to maximize the performance subject to the fairness is satisfied. In our paper, we consider binary classification. We want to predict the label zeta based on feature vector. We also have the sensitive variable gamma, which is 1 or -1. So here the z is a random data point, and we have a predictive model h sub w with model parameters w, which can return a score for each data point. So we need the performance metric and the constraint metric. So before we talk about the metrics, we need the definition. So we first need the AUC defined by subsets. We have two IID random data points, z and z prime, and two sets, g, g prime. Then the AUC with respect to g and g prime is defined as this conditional probability. And we use the standard AUC as a performance metric, which is just when the g equals the positive data set and the g prime represents the negative data set. We use AUC as a performance metric because AUC is better for imbalanced data set. For the constraint metric, we consider AUC-based fairness metric. So given 4 sets, G1, G2, G1 prime, and G2 prime, the AUC-based fairness metric with respect to these 4 sets is defined as the absolute value of the difference of AUC of G1, G1 prime, and AUC of G2, G2 prime. So our formulation is a constraint optimization. We want to maximize the standard AUC subject to the AUC-based fairness constraint is satisfied. However, this equality is strict, so we want to relax it to inequality constraint. So here we introduce a kappa which can represent the level of fairness. As the kappa gets smaller, the model becomes fair. So let's first look at the objective. We want to maximize the standard AUC, which is we want to maximize this conditional probability. And it is equivalent to minimize this conditional probability. And then it can be written as minimize the conditional expectation of indicator functions. Since the indicator function is discontinuous, we approximate the indicator function by a continuous surrogate loss function. Following the similar formulation, we can also write the constraints as the expectation of conditional surrogate loss. Then we can let the surrogate loss be a quadratic loss according to Yin 2016. With the quadratic loss, we can write the conditional expectation as a min-max formulation, while where the capital F and capital G is defined as this formulation. So thanks to this min-max formulation, we don't need a paired data set anymore. And with this min-max formulation, we can write the original formulation as a min-max optimization with min-max constraints. So here we use X represent W, AI, and BI. And the original formulation becomes minimize F0 subject to F1 and F2 smaller than or equal to 1 plus kappa. We solve this min-max optimization with min-max constraint with level set method. So first, based on Nest Rule of 2003, the level set function is HR, which is minimize PRX. Well, the PRX is defined as max over F0 minus R, F1 minus 1 minus kappa, F2 minus 1 minus kappa. Here R is a level parameter. If we want to use level set method, we need the following assumptions. So first is the strict feasibility, and then we want the expectation of capital F plus alpha times expectation of capital G is convex in X for any G, G prime, and alpha. The third assumption is we want the expectation of gradient is bounded. So under the strict feasibility assumption, we can see that the level set function is non-increasing and convex in R. So this graph is for the level set function, HR. And from this graph, we can see that the HR has a unique root at F star 0. And if R smaller than F star, the HR is positive. If R larger than F star, the HR is negative. So the level set method is generate a sequence of R convergent to F star by a root finding scheme. However, we need an oracle to update the RK. So we define a stochastic oracle of HR if given R larger than F star and a tolerance epsilon A, the algorithm can return an upbound and X bar such that these two conditions are satisfied. So here, this oracle can be an algorithm for the level set subproblem, which is minimize PRX. So this is the graph of the process of level set method. So suppose we start from RK, and based on this RK, we can compute the URK, which is negative, and then we update the RK plus 1 by RK plus URK, so which means that we move to the left-hand side of RK. So, and similarly for RK plus 2. So from this graph can show that the sequence of R is convergent to the root if the RK minus F star smaller than epsilon, XK is a feasible and epsilon optimal solution. So as I mentioned before, we need a oracle to solve the level set subproblem. So recall that this is a subproblem formulation, and the correspond this is the formulation for our problem, and the corresponding subproblem is we want to minimize the PRX, so which is minimize over X and max over Y tilde belong to a simplex. And if then we plug in F0 to F2, we can have the formulation in the last line. So here the problem is that this formulation is not jointly concave for the dual variables Y tilde and alpha, which means that the standard update for these dual variables may not converge. So to solve this problem, we can let alpha tilde equals Y tilde times alpha. So the original formulation can be written as the second line, which represent in Y tilde and alpha tilde. So this is called the perspective function. So observe that this perspective function is jointly concave in Y tilde and alpha tilde. So then we can update the dual variables. So just for simplicity, we define Y equals Y tilde and alpha tilde, and the original formulation can be simplified as min over X max over Y phi xy minus dy, and phi xy dy is defined as the following. So then we can apply the stochastic mirror descent. So first we sample the random data point zt, and then we do the stochastic gradient descent for the x and stochastic gradient ascent for the y. So here the V is a special divergence defined as this formulation, which allows a closed form update for the dual variable y. So next, I will talk about the convergence theory. So the first theorem is about the stochastic mirror descent. So if we let the eta and tau be a constant divided by a square root of t, we can know that if we have enough iterations, then this stochastic mirror descent is a stochastic oracle for the level set function hr. And the second theorem is if we suppose the stochastic mirror descent with enough iterations is used as the stochastic oracle of the hr, then the xk equals x bar returned by the stochastic mirror descent is a feasible and epsilon optimal solution after these iterations. This is the total complexity. So next, let's look at the numerical results. So here we consider the three data sets: adult, bank, and compass. And we consider convex case and weakly convex case. So we also have some theoretical results for the weakly convex case, but due to the limited time, you can go to the paper for detailed theory. And here I just show the numerical results. So here we compare with three benchmarks: proxy Lagrangian, post-processing, and correlation penalty. And this is the parallel frontier by each method in convex case. So here these three columns represent three fairness constraints, and from these results we can observe that most of the time our algorithm can have a better performance than the baselines. So our algorithm is level set, the blue line. So similarly, for the weakly convex case, we can also observe the similar results. Okay. That's all. Thank you.